Welcome to the class. Here in this class we can discuss more about the singularities of an analytic function and the residues of a function f of z and residue theorem. Laurent expansion, Laurent series expansion. A function given a function fb analytic in the given annulus r1 less than mod z minus a less than r2, then the series expansion is of the form f of z equal to sigma n is from minus infinity to infinity an into z minus a to the power n, where the convergence is absolute and uniform in compact subsets r1 less than or equal to mod z minus a less than or equal to r2. And moreover, the an is of the form an equal to a suffix n is 1 by 2 pi I integral over gamma f of z by z minus a to the power n plus 1 dz, where gamma is a circle with the modulus z minus a is equal to r, with a center a and radius r. So this kind of a series expansion is called a Laurent series expansion around z equal to a. Okay, let us see this example. Expand f of z equal to 1 by 1 minus z in terms of negative powers of z, which will be valid if in the region mod z greater than 1. So we have the binomial expansion 1 plus z square etc. that is valid when mod z is less than 1. So here we have to expand this in the region mod z greater than 1. So we first note that 1 minus z can be expanded as by taking minus z outside, we will get 1 minus 1 by z inside. So when this 1 minus 1 by z raised to minus 1 expand, we will get this in terms of 1 by z, powers of 1 by z. So that lies in the region mod z greater than 1. So from here we have 1 by mod z is less than 1. So finally we have to get it in a series expansion of 1 by z term. So f of z can be written as minus 1 by z into 1 minus 1 by z. So again 1 minus 1 by z raised to minus 1 expansion is 1 plus 1 by z plus 1 by z square plus etc. So this is valid for mod 1 by z less than 1 and that is mod z greater than 1. We have classification of singularities based on their the powers of 1 by z minus a powers. So let f of z is equal to sigma n equal to minus infinity to infinity an into z minus a raised to n be a Laurent series expansion of f about an isolated singularity z equal to a, then if f has a removable singularity at z equal to a, then a minus n, that means 1 by z powers, all the negative powers of z are 0 for all n greater than or equal to 1. And if f has a pole of order m at z equal to a, then a minus m power is not equal to 0 for all n greater than m. Okay, we have the maximum, its minimum power is 1 by, yes, 1 by z minus a to the power m. If f has an essential singularity at z equal to a, then there are infinitely many a minus n not equal to 0 terms, means infinitely many terms that containing negative powers of z. Singularities. Consider this example. A complex valued function f of complex variable is singular. A function at a point z equal to a is said to be a singular point if it is not analytic at that point. The function at z equal to a is not analytic. But every neighborhood of z equal to a contains points at which f of z is analytic. For example, f of z is equal to 1 by z. So here the function z at z is equal to 0, the function does not exist. So it is not analytic there also. So z equal to 0 is a singular point of this function f of z. Cos z and sin z are entire functions. They are continuously differentiable functions. So we can say that they have no singular point. But tan z is not entire. We can write tan z as sin z divided by cos z. So this function does not exist, or the function is not analytic in the region where cos z is equal to 0, at the points where cos z is equal to 0. The function is not analytic when cos z is equal to 0. So that points are when plus or minus pi by 2 and plus or minus 3 pi by 2, 5 pi by 2, 7 pi by 2, etc. At that points, the function is not analytic. All other points, the function is analytic. So we can say that this function tan z has singularities at the points plus or minus pi by 2, plus or minus 3 pi by 2, plus or minus 5 pi by 2. A singular point z equal to a is an isolated singularity if z equal to a has a neighborhood without further singularities of f of z. That is, a is the only singularity there in the neighborhood of that function. So, the singularity of 1 by sine pi by z. So, here the function is not defined when sine pi by z is not defined. That is, when sine pi by z is equal to 0, the function is not defined there. That happened when 1 pi by z is equal to n pi. That is, z is equal to 1 by n values. So when z is equal to 1 by n, the function 1 by sine pi by z is not defined, is not analytic. So these are z is equal to 1 by n values are n is equal to plus or minus 1, plus or minus 2, etc. are the singularities of the function 1 by sine pi by z. Is all these are isolated singularities? The function f of z is equal to 1 by sine pi by z, z equal to 0 and z equal to 1 by n are the singular points. So here we can say that each other points are singular point except z equal to 0. Z equal to 0 is isolated because in a neighborhood of z equal to 0, we can find infinitely many points from 1 by m. So all these points 1 by m are isolated, but z equal to 0 is not an isolated singular point. Of this function, f of z is equal to 1 by sine pi by z. Its singularities are 0 and 1 by n is equal to plus or minus 1, plus or minus 2, etc. So, when we take a neighborhood of z equal to 0, we can find infinitely many points, many other points, at least one point, a singular point of 1 by m. So, z is not an isolated singular point here, z equal to 0. Here, f of z is equal to sin z by z. What we can say about the analyticity or singular point of this function? So this function is not analytic where when the denominator becomes 0, the function does not exist. So at z equal to 0, the is a singular point. Otherwise, yes, in the numerator also, when z equal to 0, the function is not defined. 0 form. Function will become 0. So, we can say that this when we expand in terms of sin z, power series terms of sin z, we can find that there is no no coefficient term for 1 by z, or no terms including 1 by z. So this z equal to 0 is a removable singularity for this function. But for the case f of z is equal to 1 by z only, where z equal to 0 is a isolated singularity, but for this case sin z by z, it is a removable singularity. Z equal to 0 is a removable singularity. It's a special case. Please take it as an important one. Or we can say that z equal to a is a removable singularity of the function if limit of f of z exists at z equal to a. The limit of the function exists at z equal to a, then we can say that z equal to a is a removable singularity. When the limit of the function limit z tends to a modulus of f of z is infinity, we can say that a is a pole of the function f of z. If the function does not exist, if it is neither a pole nor a removable singularity, we can say that z equal to a is an essential singularity. Consider this example. Here z equal to 0 is an essential singularity for the function f of z is equal to sin 1 by z. Because we can see that sin 1 by z is does not the limit of limit as z equal to z tends to 0, sin 1 by z does not exist. So it is an essential singularity. Consider the two sequences I by n and 1 by n. We can see that by two-path test, limit z tends to 0 f of z modulus of f of z, that is limit z tends to 0 modulus of sin 1 by z is not equal to infinity. That is not equal to infinity. This equal to infinity is not possible there. Hence, z equal to 0 is not a pole. And again, we can use the other test, limit z tends to 0, z minus a into f of z. If z minus a into f of z is 0, we can say that it is a removable singularity. But here, limit z tends to 0, z minus a into f of z does not exist. So, z equal to 0 is not a removable singularity also. Therefore, z equal to 0 is an essential singular point. A residue of a function. When we call a function has a residue, and what is the residue of that function? Let f be an isolated singularity at z equal to a, and f is of the form sigma n is from minus infinity to infinity, a n z minus a raised to n. It's when the f of z has when we expand in power series, we will have a Lorentz part and a principal part expansion, a Lorentz part and a singular part. So when it's Lorentz expansion, the coefficient term of 1 by z is called the residue of that function. That is, a minus 1 means its negative power of 1 by z. Coefficient of 1 by z is called the residue of that function. For examples, residue of the function f of z equal to z minus cos z the whole divided by z at z equal to 0. How can we find the residue of this function? So when we expand this one in power series, we can see that the coefficient of 1 by z is minus 1. So the residue of this function is minus 1. And the residue of the function f of z is equal to cosec 1 by z. At z equal to 0, when we expand this function, you can see that the coefficient term of 1 by z is 1 by 6. So its residue is 1 by 6. Similarly, for the function f of z is e raised to z minus 1, the whole divided by z. Its residue is 0. Means there is the coefficient of, there is no term of 1 by z. Residue theorem. Let f be analytic in the region G except for the isolated singularities except at a particular points a1, a2, etc. am. The function is not analytic. If gamma is a closed rectifiable curve in G which does not pass through any of the points ak, and if gamma is identically equal to 0 in G, then 1 by 2 pi I integral over gamma f of z dz equal to sigma of the binding number n gamma ak into residue of f of ak. If it is a simple pole, the given is a simple pole, then residue of f of z at a is limit is. If the given function has a pole of order m at z equal to a. If the given function has a pole of order m at z equal to a, then residue of f of z at z equal to a is 1 by m minus 1 factorial d raised to m minus 1 by dz raised to m minus 1. It's m minus 1th derivative of z minus a raised to m into f of z at z equal to a. That will give you the residue value. Identify the singularities of f of z equal to 1 by z square into z square plus 9 and find the residues at each of them. So the first one at z equal to 0, z equal to 0 has a power 2. So z equal to 0 is a pole of order 2. And again here z square plus 9 means z plus 3i into z minus 3i, we can factorize them. So plus 3i and minus 3i 0 are its poles. Here z equal to plus 3i and z equal to minus 3i are simple poles, and z equal to 0 is a pole of order 2. So for z equal to 3i, the residue of the function at z equal to 3i is limit z tends to 3i, z minus 3i into f of z. That is 1 by 54i. And residue of z is equal to minus 3i is minus 1 by 54i. And residue of z equal to 0, since 0 is a double pole, is a pole of order 2, we use this formula and its residue will be 0. Evaluation of improper integrals. Improper integral of a continuous function f of z over the semi-infinite interval 0 less than or equal to x less than infinity is defined by the equation integral 0 to infinity f of x dx is same as limit r tends to infinity integral 0 to r f of x dx, where x lies between minus infinity to plus infinity. So the integral can be rewrite as integral minus infinity to infinity f of x dx is equal to limit r1 tends to infinity integral minus r1 to 0 f of x dx and limit r2 tends to infinity integral 0 to r2 f of x dx. When both the limits exist here, we can say that the integral converges to their sum. Show that integral minus infinity to infinity x square by 1 plus x raised to 4 dx equal to pi by root 2. So we have to find the integral of integral minus infinity to infinity x square by 1 plus x raised to 4 dx. So evaluating this as a real integral is very difficult. So we can integrate it as a complex integral. So we can rewrite the function as f of z is equal to z square by 1 by z raised to 4 and find the singularities of that function. So we can see that it has poles at z raised to 4 is equal to 1, that is e raised to I theta I, that is equal to theta 1 is equal to pi by 4, 3 pi by 4, 5 pi by 4 and 7 pi by 4 are their roots, of this function. And again from that roots z1 and z2, pi by 4 and 3 pi by 4 lies in the upper half plane of the circle. Now consider the integrating over this one. So we can take R1 and R2 as the poles which lies in the upper half plane of the circle given. Now consider integrating this over a semicircle gamma of radius r greater than 1 sitting on the real axis, so that the circular part is parametrized by z equal to r e raised to I theta, where theta varies from 0 to pi, and dz is equal to r e raised to I theta d theta. So we have by Cauchy's residue theorem 1 by 2 pi I integral over gamma f of z dz equal to residue at z is equal to z1 f of z plus residue at z equal to z2. Since those are the only poles inside gamma, in particular residue of z is equal to z1 of f of z is limit z minus z1 into f of z at z tends to z1, that will give you 1 by 4 e raised to minus pi by 4 I, and residue of f of z at z equal to z2 is 1 by 4 e raised to 3 pi by 4 I. Now we expand e raised to I theta as cos theta minus I sin theta. So you will get the answer as 1 by 2 pi I integral over gamma f of z dz equal to minus I by 2 root 2. Now on the other hand we have 1 by 2 pi I integral over gamma f of z dz is equal to 1 by 2 pi I integral minus r to r x square by 1 plus x raised to 4 dx plus 1 by 2 pi integral 0 to pi r2 e raised to I 2 theta by 1 plus r raised to 4 e raised to I 4 theta r e raised to I theta d theta. Now letting r tends to infinity, the first integral that converges to 0, that will goes to 0, that is modulus of 1 by 2 pi integral 0 to pi r3 e raised to I 3 theta by 1 plus r raised to 4 e raised to I 4 theta d theta, that will goes to 0 as r tends to infinity. And the other part will give you minus I by 2 root 2. The answer is equal to 1 by 2 pi I integral minus infinity to infinity x square by 1 plus x raised to 4 dx. So the integral value is 2 pi I into minus I by 2 root 2, that is pi by root 2. And here you can find some references. A lecture note by Dr. Shanxi Lu and our study material, and there is other link. So do more problems based on residue theory and improper integrals, complex integration, power series and all. So best of luck. Thank you.